Okay, good morning, guys. Hope you guys can see the screen. Let me share. You guys can see the screen, right? Hello.
Yes, sir.
Yeah. All right. Okay. So the last class we saw about the quality attributes and also characteristics of embedded systems, and one of the main characteristics was that embedded systems are domain specific, right? Application specific and domain specific. So today we will see some examples or more like case studies for those two categories. Okay, first thing is we'll see about washing machine. We'll see a washing machine example for the application specific embedded system. Okay, so let's make it a little interesting. So I want you guys to describe a washing machine for me. So who wants to start? Who's there? Hey, Ganesh Shastri, can hear me?
Sir, yes, sir.
Yeah, let's start. Let's start with you, okay? And then we'll chain from you. So describe a washing machine. What does washing machine have? What are the different components? I'll try to draw. May not come out well,
Sir,
but
it,
I will see. Yeah, go on.
sir, it's a cuboid box-like structure.
Okay, cuboid box-like structure. Oh my god, I have to keep this. Okay, let me draw a box. All right, and then cuboid kind of thing. All right, is it good enough for you to understand? Okay. Then
If it's the front door, there will be a round door in the front.
okay. Ah, okay. We'll assume it's a front load. Okay. Ah, what does round mean?
Then it has,
Hmm.
so
Yeah, yeah. Go on, go on.
it has a digital
Ah,
something. Uh,
okay.
yeah, in that place we have to put powder,
Where?
washing powders.
Which place?
At there on.
Top or
Yeah,
front?
sir. In that place,
Somewhere here.
in the I think left corner.
Left corner here. Somewhere you put. Okay. So, all right. And then this
We
one.
have digit
What is this one? This round thing.
the door.
Huh?
Door.
The load, right? So you put the load in here. Okay.
We
All right.
have digital display.
Yes. Where is it?
Yeah, there only.
Here only. Okay. What display? Huh? Okay. So this is your display. All right. Then,
Then we have some buttons for
good. Okay. Have some buttons. Okay. All right. So very good. Thank you. Point to someone else. Call out a name.
Subiredi.
Subiredi.
Sir,
Yeah. So continue. What are the other things that you have in your washing machine?
wheel inside.
Wheel.
Mm,
Where? Bottom.
No, sir. Inside washing machine.
Inside. What wheel?
To rotate the wheel, not wheel kind of thing.
You mean motor?
Yes.
Huh? Okay.
Not motor, sir.
What is this? What wheel?
To rotate that, there will be something, no, sir, inside that washing machine. To rotate that cloths and all.
That's what is a load, man. That's what Ganesh already told. So that's what this is.
Oh, okay.
Okay.
Uh, don't know, sir.
Don't know.
I
Washing machine.
think,
Come on, man. Washing machine. You don't know washing machine. You don't wash your
he
clothes.
said everything.
Let's
He
become
already
anything.
said, no, sir. He already said about soup and
Huh.
all.
Okay.
So
Man, that even your housemaid will say all these things. We are talking about some engineering stuff. Let's get deeper. Let's see what is there inside of a washing machine.
uh, maybe some internal parts to regulate if the door
Yeah,
is opened or closed.
exactly. Yeah, what is that? What is that internal part?
Some embedded system
Embedded system.
to regulate.
Okay. Yeah, because we are discussing it in embedded system. Okay, let's put some embedded system here somewhere. Right. We'll put it here. It's somewhere here. Okay. I don't know why I draw like this, but anyway. Okay, there's an embedded system. Embedded system. Okay. What does it do? Then what else? Oh, no, call out someone. Call out someone.
Indraja, sir.
Indraja. Indraja.
Yes, sir.
Yeah, washing machine. You're familiar with washing machines?
No, sir.
No. Who washes your clothes?
I won't wash, sir.
You don't wash your clothes? Seriously. Who washes? I asked.
No.
You don't wash clothes and where? You buy a new one every day. Huh?
Mom will wash.
Oh,
My
oh,
mom will wash.
oh, mom will wash. Okay, okay. So you've never seen a washing machine in your house? Oh, okay.
I
So
saw, sir.
you saw. Okay. Call on. We shouldn't be spending this much time on a washing machine. Come on, guys. Okay, call out somebody who actually knows about washing machine. I think everybody, every house has washing machine, right?
Okay, okay, I will call, sir.
Call out, yeah.
Vidya.
Vidya,
Yes, sir.
come on. Can you please help
I think
Indraja?
Vidya. No.
Huh? Vidya knows. Okay, Vidya washes her clothes, so she should know. Oh yeah, Vidya, come on.
No, I don't do.
You don't know. Does this look like a washing machine to you? Like whatever I have drawn here.
Yes, sir.
Good. So
Kind of.
what do you think will make this washing machine work?
Uh, uh, can I tell the components which I know?
Yes, exactly. That's what I'm looking for. Yes, tell me.
Okay. I think a basic component of it would be a timer.
Timer.
Then,
Good. Okay. Very nice.
yeah. Then we'll be, of course, having a PCB because we need
So we
it
put
to
it as
work.
embedded system, which we'll call it PCB. Good. Okay. Man, you're on a flow. Come on. Yes.
Then a motor probably.
But you need to connect this to a motor, right? Good.
Yeah.
Okay. Yeah. Come on. Yeah. Yes.
Uh, I know this one, sir. So I thought these are the basic things. Then,
I think you did your part well. Okay. Just call out one more person. We'll see if they have anything else to add. Thank you.
sir, one more.
Hmm. Call out. Call out.
Nidhi, sir. Nidhi.
To your balcony or somewhere, utility space, and see about washing machine, right? Yeah, you guys are washing it in cell phone only anyway. Just run and see what's there in washing machine. Nidhi, you're here? Okay, Nidhi is not here. Call out someone else.
Omkar.
Omkar. Yeah, Omkar. He typically has
Hello, sir.
mic problem. Hey, you're here. Okay, great. I thought you'll have mic problem fixed. So anyway,
No, sir.
we need some help in designing a washing machine. Can you please help? So we figured out we need to put a
The
load.
power supply also.
Ah man, seriously. Okay. We need a power supply. Okay. Then anything else?
But then uh, the water supply also.
Man, seriously, right? These are the two things that you need. You know, right? Okay, so you need a water supply. Without water, what will you do? Washing machine. Okay, so we'll draw a tap. Okay. This tap, okay. Kindly bear with my drawing skills. Okay, a water supply. So water supply, okay, there is a water supply inside. Do you also have a water supply outlet? You should, right?
Yes, sir.
You should also have a water
Yes.
outlet. Yeah. Okay. So water. Is that it? Is there anything else?
Not that I can think of, sir. No.
Good. I think this is good enough for us
I
to
think
make
all of.
washing machine. Yeah. All right. So just call out one more person. Okay. You just call one more person.
Uh, Nitin, sir.
Nitin. Which Nitin?
Nitin Suraj.
Nitin Suraj. Hello. Okay.
So
Someone.
he messaged.
Or mic not working. I can't switch. I mean, like, okay, I can, but let's see. Be different. Water heater would be a good add-on. Nice. Okay. A water heater. Yeah, we need a heater too. All right. We have a heater or more like a dryer, right? Dryer slash heater. Okay. No, but I called you for a different purpose. Can you speak out, Nitin? Okay, call out someone else who can talk whose mic is working. Mic permission's not working. Yeah. Nitish Hegde. Nitish?
Yes, sir.
Yeah. Right. So I want you to like tell me what these buttons do. The display and buttons, right? Like what it does. I just want you to explain like what kind of things it does.
Like we can set the mode of washing
Mode
or
of washing. Okay. What different
and
modes of washing?
I don't know exactly, sir. Maybe something like a dry wash or something.
Oh, okay, fine. You want to dry or you want to just spin?
Yeah, there will be some mode for only 20 minutes, and then really for 15 minutes.
Okay. You guys never wash clothes. You? That
Normal.
one thing that I figured out. None of you guys wash clothes.
We do, sir.
You do. Then you should have known all these things. Okay. Okay. Apart from mode, what else is there in buttons? What are the different buttons you have?
One will be the
Water.
Huh? Huh?
start button.
Start button. Correct. Yeah. Start button. Okay. Then start or power. Right. You also have a power button. Then
Then Something will be there about the system settings.
System settings, like what?
Like if the something goes wrong with the software, then
Ah,
to make it right.
I mean, like a reset.
Huh.
Okay, reset, fine. All right, yeah. So this mode itself, we can also have one more, like the load. How much load you have? Heavy,
And
medium, uh,
water level controllers.
water level. You have a button for that?
I think it may
Oh,
be
so
there.
that's what the high, medium, low. That one, right? Okay. Oh, yeah. You want high, full water load or medium, something like that. Medium or low. Okay. Ah, good, good, good. Okay. So now coming to the display, I think this covers most of the buttons. I think we would have left one or two here, but I think this covers most of them. In display, what do you have? What do you have? What should you display?
It will display the remaining time while washing the clothes.
Okay. So what kind of display we need here? Do we need like a grand the LCD screen that we have in our cell phones?
No, sir, that no. Or some LED display will be there. No, some 7 segment or 8 segment.
7 segment only. It looks like eight, but it's a 7 segment display. Okay, great. All right. Thank you, guys. Thanks, everyone.
Welcome.
You have a 7 segment display. That's all. We have a washing machine. So you now know what washing machine has, right? It also has sometimes, right? It also has a buzzer or like a small speaker. So once it washes your clothes, right? So it's going to sing some like a symphony for you, right? It's going to signal saying, "Oh, okay, wash the clothes. Time for you to come," and then pick the clothes. So that's what it is. So if you look at this, right, so you need it's an electromechanical device. You have water flow, okay, water inlet and then outlet, and you need a power supply, of course. Okay, the power supply will go for both your embedded device as well as for your motors. Okay, you have more than one motor. Okay, so main motor is only for your I mean rotating the load here. Okay, it's called as tumble tub or something like that. Okay, and then you have a I mean soap and all these things are part of the actual washing thing. And so you also need a controller. Okay, so the other motor will be there to control the inlet. Okay, so you can't just have all the water flow into your washing machine. So you have some kind of a motor here that controls the inlet. Okay, so you fill, so based on your load you have high, medium or low. So let's say you have medium, so up to medium level you fill the water. Then you don't go and manually close the tap. Okay, this motor takes care of it. So this motor stops the inlet. Okay, and after some time, right, it does all the rinsing, everything is done. Then you need to open the valve here. Okay, so you'll have another like stepper motor or some kind of a relay to open the outlet, so the water goes away. Okay, and the rest of the time, in between time, you actually rotate your motor here that does the washing. Okay, and you also have these buttons, as we said, right? So it's going to set the mode, or it's going to tell what it does. And all you need is the simple push buttons. Okay, you don't need like a full-fledged 110 keys keyboard, correct? All you just need like a handful of probably 10, around 6 to 10 buttons. And the display, you don't you need only like a small LEDs. So in some washing machine, you don't even have a 7 segment display. You only have small LEDs for each of these buttons. So based on which button you press, next to it there is a small LED here. Okay, so that will glow. Okay, so and then once the washing is done, so you go to a state where it is complete. So you actually play music. Okay, so for that you need a speaker. So it's a combination of all your input and output devices here. Okay, sensors and actuators that we saw earlier. Okay, any questions on this, guys? So hope it's very clear, right? It's very interesting too, isn't it?
Yes, sir.
Okay, great, nice. Okay, so that's what we were supposed to see today. I mean, it's not all. It's only one topic we have covered. Okay, so as we can see, I'm not going to go over all these things. So they've just listed all these items, whatever we discussed now. So this is a typical washing machine, whatever we discussed, right? It's here. It's called the inner tub and outer tub. Yeah, okay. So yes, we have and water in pipe outlet and all these buttons, LED display, and this is the lights, right? I mean the LEDs that I was talking about. So you may or may not have this LED display, but yeah, anyway. Okay, that's great. So the next example we are going to see is automotive. It's a domain specific example. So this deals with the automotive industry altogether. Don't worry, I'm not going to ask you about to describe a car here. Okay, so we just quickly see. Oops, what is there? There's no figure here. Okay, so what's there in automotive system, right? So what are the different things that we see in a car? Let's take a car for example. Okay, so one thing is, so we'll have a simple mirror and wiper control. Okay, and then you also have a complex airbag control or anti-lock braking systems and everything in between. Okay, so any button that you push in your car, so that connects to an embedded system. Okay, and these embedded systems are independent, like meaning they work independently of the other. So for example, your mirror control is independent of your wiper control, and that is independent of your airbag controller. Okay, so these are all like several controllers acting independent of each other. And in very high end cars you also have some kind of a central monitor like a CPU that monitors all these embedded system to check whether they are functioning or not. Okay, and mostly they are DSPs, or they are combination of microcontroller and DSP. Okay. You also have your sound system, navigation system, and all these things, right? Everything has an embedded system. So these embedded systems are called electronic control units or embedded control units. So however you want to call it, ECUs is what they call. Okay, and so they can be high speed and then low speed. Okay, so high speed components control units are for critical systems, like for example your fuel injection, anti-lock braking system, your airbag system, and all these things. Okay, so they're very critical. You need high speed here because you don't want them to miss the deadline. As we saw, embedded systems are always driven by deadlines. The moment you push the brake, it has to work, the brake has to take effect. Okay, so for that you need high speed electronic control units for these critical embedded systems. And for the other ones that are not so critical, right, what are the other not so critical things? So you have your audio controller, driver, door locks, and then door glass control and all these things, right? So it's okay if you push the button, it takes a little longer, you miss the deadline, it's also fine. It's only going to cause a little discomfort, not going to endanger anyone's life. Okay, the next most important thing about these automotive embedded systems is the communication. Okay, so how are communication how does communication happen? So you have a few protocols here, similar to what we have seen in the earlier module, right? So one most popular one is a controller area network, CAN. Okay, so this CAN is a very popular automotive communication protocol. So these are the ones that actually takes care of the safety system, the communication between the safety systems, right? Like your airbag and anti-lock braking systems and all these things. This CAN has evolved so much that they are actually talking about vehicular networks, right? Vehicle to vehicle communication. So CAN, the later versions of CAN even supports that. So you can, so for example, you want to communicate something to a driver ahead of you, you can. Okay, so and also it can talk to the like infrastructure. So your cars can actually talk to your traffic lights or something like that. Okay, so those kind of things also this can supports. The other one is LIN. Okay, so LIN is local interconnect network. So this is a little low speed So this is used for the not so critical applications that we saw. And finally, we have most is media oriented system transport. So here it is it's a multimedia fiber optic point to point network. Okay, so this is also these are the three different protocols that are popular in use. Okay, so that's about it. Any questions, guys, on this? So this particular chapter, what we saw was we saw two examples. So one is application specific, which is your washing machine, which is specific to your washing the clothes, right? It cannot be used for anything else. It cannot be used for cooking your food. So that's very application specific. The other example that we saw is your automotive sector, where your cars or other vehicles, right? So what kind of uh, uh, domain, I mean, the automotive domain that they support. So, what are the different embedded systems that are involved in that? Okay. So, if there are no other questions, then we'll move on to the next chapter. So, we'll just have a brief introduction to the next chapter. So far, what we have seen is the uh, yeah, we saw characteristics and quality attributes of embedded systems in the previous lecture, and which included operational, non-operational quality attributes. And in this I mean today's lecture, we saw the embedded system application and domain specific examples. Okay, and today we are I mean for the rest of the class we are going to cover some topics in the hardware software co-design and then program modeling. Okay, so we'll just get started. Okay, so embedded system development approach and then hardware software co-design approach. Okay, so these two topics we'll be covering. Okay, so coming to the hardware software code design, right? So embedded systems, as we saw, embedded systems mainly has lots of these embedded components like hardware components. It may be both electrical, mechanical, and it also has the electronic hardware components. The other one is the software part. So as we saw, when we have your push buttons and display, right? So you need some kind of a firmware or drivers to run these hardware. Okay, so slowly, I mean, like embedded systems started having evolving from having very small firmware and ROMs all the way up to even like operating systems that actually manage different tasks. Okay, so so you need some kind of a hardware software code design when you develop an embedded system. Okay, so you need to divide which parts go to hardware and which parts go to software. Okay, so then you have again architecture for both. You have hardware architecture, software architecture. And so one thing to note here is that when you're the company, right, like which manufactures this embedded system, you'll have your hardware team and the software team. Okay, and it will not be like first the hardware team will work and then they will get all the hardware up, and finally the software team will I mean embed the software. No, it doesn't work like that. So both of them work actually parallelly. Okay, so it's like there is a very close like sorry, there's less interaction between the two teams, meaning they work independently, but once in a while they actually have to sync up so that they don't miss out on any of the bugs. Okay, so they actually have to work closely. Okay, so it starts with your requirements. Okay, the product always starts with the requirement. You again take a washing machine for example. So you'll first like enlist all the requirements from the customer, and then you will make it a little more. You'll actually make it little more crisp by putting in your technical jargons into it. Okay, so your for example, a washing machine, the customer might say, so I need like 10 kg of my clothes to be washed in this washing machine. It's like a very huge thing, right? So then how does it convert to? So then you need to fix the motor, and you need to have like the torque of the motor matching this, and you need a driver component to drive that big motor. Okay, so you convert that into the technical aspect, and then you make a system level need, right? So you write down the technical requirements of the customer requirement. Okay, and then the system level processing requirement transfer to the functions that can be simulated and verified against performance and functionality. So you start with again you simulate it. So you actually kind of come up with a simulation model to verify whatever your requirement is, right? Will work on this, and only after this particular step is done, then you start with your architecture design, meaning like you actually design the system, like what components go in here. Okay, so and then you draw the block diagrams, and then you see which system interacts with what, and things like that. Okay, so once that is done, then you actually decide whether these systems go should be done as a hardware or a software component. It is technically possible to go for 100% hardware, but the problem will be it will be less flexible, meaning if you want to change something in the future, you may not, right? So then you need to bring in a firmware component or a software component to it, and you see like how you can partition, like how much you want it to be hardware, and how much you want to port it to software. So you have so these things to be covered. So these are the issues that you need to take a decision on, like the model selection. So what are the different components models that you want to buy for this system, and then the architecture selection. Okay, and then the language selection, and partitioning of hardware and software. So these are the things that are very important. Okay, so when you take a model selection, all right, how much time we have? I'll just take another 5 minutes or so. Okay, so model selection. So this model is not about just the hardware model, right? So when you want to design a system, that you need to represent the entire embedded design in terms of some kind of uh, like an illustration. Okay, so you can, so the examples of this includes your data flow diagram and control data flow diagram, or data flow graph, control data flow graph, or it can be an object oriented model, or it can be a sequential program model, and there are so many other models how you can like represent this system as an illustration. Okay, and the next one is the architecture selection. We'll again go in detail about the architecture selection later, but to give you a glimpse of it, it's the architecture. What kind of architecture are you going to support? Are you going to use a CISC architecture or a RISC architecture, or is it going to be a VLIW? So VLIW is nothing but very long instruction word. So where you have multiple instructions embedded in one instruction itself, like meaning it's a much more complex instruction. So what you will have here is so you have let us say uh, you always have matrix multiplication kind of scenario, right? So if you have that, then what you will do is you always will have one multiply instruction, and then you have another multiply instruction, and then you will have an add instruction, and followed by that you will have a store instruction. If you have this sequence occurring every time, then all these instructions, right, will be embedded in as a single instruction. Okay, your architecture is going to support that. So in your ALU will not just have a multiplier unit, but then you will have your multiplication unit followed by another multiplication unit followed by an addition unit, and then you will also have a store unit. So all these things will be done in one shot. Okay, so that's really helpful in many, especially in DSP kind of applications. It's very useful. Okay, and you have your SIMD and MIMD instructions, like single instruction multiple data, and this is mostly useful for pipelined processing, and MIMD is again useful for your DSP applications. Okay, so you have different other architectures, so we'll go in detail later. Coming to language selection, you have then you need to decide on your language, which language are you going to use, right? So this is typically like how you do your mini projects also, right? So you start with your problem statement, and then you buy the components, then you actually see, okay, so what kind of software are we going to use? Is this going to be C based, C++ based, C sharp, Java, so many things. And these are for the software side. For the hardware side, right? So you can implement it in Verilog or VHDL, System C, and so many other things. Right? So you need to have some kind of decision at this time, like what kind of language you're going to use. It also depends on what model you are using. For example, if you're using object-oriented model, then it makes sense for you to switch to C++ or Java. Correct? It doesn't make sense for you to go to C if you have object-oriented model. So things like that. And finally, what we talked about, right, like partitioning system requirements into hardware and software requirements. You need to finally draw the line. What are the components that goes into hardware? What are the components that goes into software? Okay, so these are the different things that are very important, or the fundamental issues when you come when you discuss the hardware software co-design. Okay, so all right, I have a couple of more minutes, so let me see if we can just look at your data flow diagram and control flow diagram. Okay, so it's very simple, so that's why I'm just going forward. Okay, it won't take much time. So computational models, right? So we saw some examples, data flow graph or data flow diagram. I'm not going to go through the text here. It's very simple. Okay, so let's say you have some model requirement like this, right? You have two instructions, x equals to a plus b, and the other one is y equals to x minus c. How can you represent this? This can be represented as a data flow graph, where your nodes, right, each node in the graph is going to represent the operation, and also your edges are going to represent your variables. Okay, so then you represent this x equal to a plus b like this. So this edge becomes x, and these two edges become a and b, and then the node is the addition. Okay, so here x equals to a plus b. Now you have y equals to x minus c. Okay, so which means that you're going to have like one node here with which is a subtraction minus, and then you're going to do x minus c, which becomes y. Okay, so that's all about this, right? It's very simple, and it's called a data flow graph or a data flow diagram, however you want to call this, right? And there's also this particular example, it's called as acyclic data flow graph because there are no cycles. Okay, there are no loops, right? So it becomes an acyclic graph. You can also have cyclic graphs or non-acyclic graphs, right? So when you have your input going back, I mean the output going back to one of the earlier nodes, so then you can represent loops in here. Okay, so this is an example of non-acyclic data flow graph. Then we have something called as a control data flow graph. So then, as the name suggests, right, it has an additional component of control. What is a control? If you think about it, your entire program, right, your however complex it is, it is just a data flow graph. How much ever complex program you write, it is just a data flow graph. In addition to the data flow graph, you will have one if condition. That's all it is. Okay, so if you have one if condition support, then your data flow graph with an if condition support can represent any complex program that you have written. Okay, so this is nothing, control data flow graph is nothing but your data flow graphs with a control statement. Okay, so for example, if you have if flag equals to 1, then x equals to a plus b, else y equals to a minus b, can be represented like this. So we've seen flow charts, right? So it's something like a flow chart, but the only thing is you have a data flow graph here and a flow chart embedded into it. Okay, so with this we will stop today's class. Okay, hope these are clear. Okay, any questions, guys? Any questions? Okay, so hope it was interesting. Okay, today's class we saw an example of washing machine, and also we saw how cars work, like different components of embedded systems in cars. Different embedded systems in cars. And we also saw hardware, software co-design, and we ended the session with your models, right? Like different model, like data flow diagram or data flow graph and control data flow graph. All right, if there are no other questions, then we'll stop here. Okay, you guys can give your attendance and free to leave. Thank you.
Good morning, sir.
Yeah.
Excuse me.
Yes.
Yeah. Sir, actually in MC lab, we were asked to write the records. So the problem is we don't have our records at our home. So how is it like we can't write?
Okay, I'll talk to ma'am and I'll figure that out.
Okay. Thank you, sir.
Please drop me a message, right, so that I don't forget.
Yeah, sure, sir.
Thank you.